Okay, in this video we're going to talk about rates of reactions. So what the rate of a reaction is and what different factors affect the rate of reaction. So the simplest definition of rate, the rate, as you probably know, simply means how fast. So the rate of anything is how fast that something happens. And what that means in chemistry is not how quickly in a reaction will the reaction finish. It is a bit more precise than that because some reactions are reversible, as we've seen previously, and therefore they will never fully finish. They go one way and they could go the other way. So we need to work out a more complete definition. And so what we actually look at is the amount of a reactant which is used up, or the amount of a product formed, and how long that takes. So quite simply, our equation for our rate is equal to amount of reactant used or product formed. So amount of reactant used or product formed divided by your time. Now you'll notice I haven't told you which units this is going to be in, and that's because it absolutely depends on what you're measuring. If you decide to measure in grams and the time in seconds, then the rate would be in grams per second. If you decide to measure in moles and per minute, then your rate is going to be measured in moles per minute. And so depending on what you are measuring, the unit for the rate of reaction will change. So I'm not going to give you an exact unit at the moment. And one thing which might confuse you is, why do we have reactant used or product formed? That is because we choose the one which is easiest for us to measure. And I'll give you a couple of examples. Now this is a reaction you would have seen before. If we begin with calcium carbonate, which is obviously the main component of limestone, and we break that down with heat, we are going to get calcium oxide plus carbon dioxide, CO2. And this is the thermal decomposition reaction that you have come across before. Obviously we have solid calcium carbonate, we have solid calcium oxide, but carbon dioxide is of course a gas. And now this is important when it comes into measuring the rate of reaction, because if I was carrying out this reaction in a test tube in a lab, say, how would I know that I've gone from calcium carbonate to calcium oxide? Because if, for example, they were the same colour, then I wouldn't really be able to tell. I'd have a solid and then I would end up with a solid. And importantly here is, because carbon dioxide is a gas and we are producing carbon dioxide every time that we react calcium carbonate with heat to make the calcium oxide and CO2, that means that measuring the amount of CO2 given off is a direct measurement of the reaction occurring. And so therefore, we could plot the amount of gas given off, so volume of gas. Okay, so obviously we start off with no gas because it's all solid calcium carbonate. So volume of gas given off against time. And we give that appropriate units. Volume of gas is normally in decimeters cubed, and time, in this case I'm going to say seconds. And I'm most likely going to end up with a curve that looks something like this. So at the start, loads of gas is being given off, and then as the reaction proceeds and proceeds, it starts to slow down and slow down and slow down, and you'll get this scenario occur here. What's actually happening is loads of gas is being given off at the start of the reaction, and as the reaction goes on, we have less and less calcium carbonate to break down because it's already reacted. So less and less gas is given off, less and less and less, and eventually this is going to get flat, so we have the same volume of gas left because no more calcium carbonate is actually reacting. This gives us an exact measurement of the average rate of a reaction. We can measure the average rate at any point on this curve. Let's say, for example, I took this point here, and let's say this was at time 10 seconds. So this was at 10 seconds, and the amount of gas that I've given off is, I don't know, let's say 5 decimeter cubed. So after 10 seconds, 5 decimeter cubed of gas had been given off. From our rate equation, you'll remember that the rate is equal to the amount of reactant lost or product formed. In this case, we've got product formed, which is gas. So gas formed divided by time. And using our real numbers, we have given off 5 decimeter cubed of gas, and that has taken 10 seconds. And so therefore, we have 5 divided by 10, which is just a half, or 0.5 decimeter cubed, because that's the volume of gas, 0.5 decimeter cubed per second. Now, you'll see that the units of the rate directly reflect the units of the volume of gas and the units of time as well. If this had been in centimeters cubed and this had been time in minutes, then we would have had centimeters cubed per minute. Another way, if you have a solution, let's just quickly draw a beaker. Let's say if you had a solution like this, which was clear and colourless, let's say your reaction formed an insoluble solid. Insoluble solids in solution make the solution go cloudy. Eventually they'll precipitate and layer at the bottom, but when they're all mixed around and flowing around, they go cloudy. That's why a lot of water in rivers, you can't see the bottom of the river. That's because there's so many solids all in the water which block your view, and so it goes cloudy. The same can happen here. So if we formed a solution which was not colourless and it went cloudy like this, this is because there's solid dispersed throughout there. We can actually measure the rate of reaction by measuring how much light can pass through the solution. Let's do that in yellow. If we are looking at light, we shine light onto here. It's meant to be in 3D. We shine light onto a colourless, clear solution. The light will go straight through, and so it will be transmitted. If we shine light onto here, well, the solid particles in here, which make the solution cloudy, are not going to let a lot of that light through. That's why if you close your curtains, the light doesn't come through, because the solid stops that light coming through. And so we can actually measure transmittance of light. And so we would have axes which look like this. We'd have light transmittance on the y-axis, and of course again we'd have time on the x-axis. And now if you think about this situation, to start with, our light is fully being transmitted. So light transmittance is going to be very high at the start of the reaction. And as the reaction proceeds, the light transmittance goes down and down and down and down. And that is because the solid product is being formed. And so we'd have a scenario where we have light transmittance starting up here, and it goes down and down and down and down and down, and eventually it's going to level out at some point. It might not be as dramatic as that, but it might be. So the amount of light being transmitted in a given amount of time is telling you how quickly your reaction is actually proceeding. And so in exactly the same way as we did above, we could take a point here, right? And we could say, what's the difference in light transmittance from here to here? And let's say that this is 100%, and this is, I don't know, 40%. Your light transmittance has gone down, therefore, by 60%. And that would be over a certain amount of time, and this might be in 5 seconds. Okay? And then you don't need to worry about units of light transmittance and things like that. You just need to be aware that we can use that in order to work out how much of a substance has reacted. Okay, so now we've had a look at exactly what the rate of a reaction is and how we measure it. Let's have a look at what actually affects the rate of reaction. How can we increase or decrease the rate of any given reaction? And the key here is something which you will have heard of, which is called the collision theory. Collision theory. Now this does require you to know the basics about what makes up a substance, so in terms of the atoms, and to know that the atoms are constantly moving around in gases, liquids, and not so much in solids, they're more vibrating. And the first feature which I want to talk about, which affects the rate of reaction, is the surface area. the surface area. So if I have marble, marble is actually made up of limestone, which is of course made up of calcium carbonate. The limestone has changed in order to form marble. Let's say that in purple, this is going to represent just an atom or a molecule. It doesn't really matter. If I had solid marble, let's say a solid box of marble like this, the marble is made up of all these atoms all lined up in a nice arrangement like this. Okay, and so the box I've drawn around it is just to show you that this is a solid separate on its own. Now, the surface area of this could be greatly increased. For example, if you had, you know that sugar that you get out of a packet is very finely ground up. Caster sugar is even finer, and you can also get sugar cubes. If you put a sugar cube in a cup of tea, the sugar cube doesn't disappear just instantly like that. However, if you put small grains of sugar from a teaspoon into a cup of tea, it dissolves straight away. And what's the difference there? Well, the difference is that the grains of sugar, or the little crystals of sugar, have a way higher total surface area than their equivalent cube of sugar. So if I had exactly the same mass of this marble, but ground up into chips, I might have just little chips like this. So this is the same thing, but smaller pieces. And so you've got these smaller pieces of marble and these large pieces here. These smaller pieces, you'll notice that every one of these small particles, doesn't matter what they are really at the moment, every one of these is actually exposed to outside, to the elements. So that means if I add something to it, then they will all be able to be accessible and they'll all be able to react. Whereas in this here, if we have a look at these atoms here, I'm just going to shade them in. These atoms here are completely surrounded by the atoms or particles which are above, below and side to side. And that means if I added something from the top, then it's not going to directly hit these. So it's going to take time for everything else to react or dissolve or whatever I'm going to do in order to reach these down the middle. Whereas obviously the case here is that they can all be reached at the same time. And that is the reason why the reaction is going to be quicker. So, what I'm going to do is I'm going to add hydrochloric acid, so HCl. So if I add hydrochloric acid here, do that in red, then this top part is going to start reacting. So these are going to react, and after a while when these have all reacted, then these are going to react, and so on, and we'll work our way down. If I add hydrochloric acid this side, well, they're all going to react at the same time. And so which one is going to be quicker? This one is going to be way quicker, because these are all going to react at the same time, and then the reaction will be finished. Here, these guys at the bottom have to wait for all the guys at the top, all the guys at the top to have already reacted. And so therefore, it's going to take way longer. So that is why surface area is going to increase your rate of reaction. So increase SA for surface area, you increase your rate of reaction. Okay. Right, so the next condition which is going to change the rate of reaction is going to be your temperature. So, temperature here. What I've drawn here is two separate substances. We don't really care what they are, but let's say you have these red particles and these blue particles are going to react with each other. Now, the collision theory states that for a reaction to occur, the red and the blue particles are going to have to collide. So, bang, like that. And then if they collide with enough energy, and that energy is known as the activation energy, then these two guys will join up and they will become, well, they will react, and obviously you will form a product. And now these can buzz around as their final product. Okay, so that's what actually is happening in a reaction. If these two don't hit each other with enough energy, so let's say that this red guy Doesn't really have much energy, so he's ambling along slowly. And he hits this blue guy, but there's not enough energy. You don't have at least the activation energy in order to form the reaction, in order for the reaction to occur. So he hits this blue guy, but no, not really feeling it, so he just leaves. The blue guy can just leave as well. And so a reaction there hasn't actually happened. We need to increase the energy that each one of these guys has in order to cause the reaction to occur more often. And if it's occurring more often, then it's going to happen faster. The way we do this is by increasing the temperature. So when the temperature goes up, these red guys and the blue guys, they will start buzzing around quicker. So they'll have more kinetic energy and they'll start buzzing around quicker. And if you think about it, if all of these guys were all buzzing around quicker, you are going to get them hit each other more often. It's like if you've ever done bumper cars at the fairground, if everyone was going 1 mile an hour, how often would you crash? Not very often. But if everyone was going 40 miles an hour and you're in a small space, then you're going to hit each other all the time. And so that's what's going to happen here. Because everything's moving around quicker, things are going to hit each other more often. So the first part is how often they hit each other. The second is that because they are moving faster, they also have more energy. So more energy. And remember, they need at least the activation energy in order for a reaction to occur. And so, if we have these guys moving really fast, there we go. This guy's moving really fast with loads of energy, and the blue guys are doing the same thing. I can't do it all at once, but they hit each other, boom, that is going to cause a reaction. So now, these guys can travel away as a molecule because they reacted. Because it's happening more often and with a higher amount of energy, you have a double-edged sword, really, if you like. The more often that collisions are going to happen, the higher the rate of reaction, and the more energy each particle has, the higher the rate of reaction. When you increase your temperature, you increase how often they're going to hit each other, and you increase how much energy they all have. And so therefore, you are affecting two things at once. And so, just so you're aware, an increase in about 10 degrees Celsius will approximately double your rate of reaction. So every time you increase the temperature by 10 degrees Celsius, your rate of reaction will roughly double. And so that is very powerful. Now there is another way of increasing how often the particles are going to collide. And that is by increasing the temperature, increasing the concentration or the pressure. So, concentration or pressure. The reason why concentration and pressure are grouped is because pressure is basically the concentration of a gas. And so concentration is when we're talking about solutions, so like salt water will have a concentration, your hydrochloric acid will have a concentration, whereas if you then turn hydrochloric acid into hydrogen chloride gas, that will then have a certain pressure. If you increase the pressure, it's just like increasing the concentration. Okay, right, so same scenario, we've got these purple guys reacting with these yellow guys. And so if the temperature remains constant, here we have quite a big space, and these guys will just be moving around like so, and eventually they might bump into each other and a reaction will occur. But it's going to take a little while. They've got quite a lot of room to move around here. They're being let do their own thing. And so your speed of reaction is going to be fairly low. The rate of reaction is going to be fairly low because the collisions are not going to happen very often. Now, let's go down. This would be the scenario if your concentration or your pressure was increased, because then you have the same amount. You see, I've only got 3 yellows and 3 purples, same as above. Same amount, but in a much smaller space. That is what pressure and concentration mean. And so now, even if these guys are going at the same speed as they were above, what's the likelihood that they're going to bump into each other in here? Well, way more likely, because they have far less room to actually escape each other. Up here, there's loads of free space and they can escape, whereas down here, there isn't. And so that means the collisions are going to happen way more often, or way more frequently, and therefore the rate of reaction is going to increase. This increase is not as drastic as it was with temperature, because increasing the concentration or the pressure doesn't increase the energy of each one of these particles. Increasing the temperature does. So that's why the temperature shows a more drastic increase. But concentration and pressure, increase both of them, then you're going to increase your rate of reaction. And so finally, we're going to talk about something known as a catalyst. Now, a catalyst is something which will speed up the rate of reaction. You've probably already learnt that. But what a catalyst actually does and how it does this is it reduces activation energy. So remember I said activation energy is the minimum amount of energy required in order for the reaction to occur. If that goes down, that means that particles which before didn't have enough energy to react, now, well, they will. And all the other particles which were going to react anyway will still react. And so now you've got more of your particles able to react. So let's have a look at this situation. I've got these green guys reacting with these blue guys. Now let's just say, for example, these guys in the corner, they have enough energy to react. But everyone else, so everyone else here, doesn't. That means these guys buzzing around will never cause a reaction. Eventually, boom, this reaction will occur. And so it's going to happen fairly slowly because a lot of your reaction just isn't going to happen. So the rate of reaction is not going to be very high. On the right hand side, this red line here represents a catalyst. We've got a catalyst in here. And so the activation energy has gone down. In this case, we only have two guys, let's say these two, don't have enough energy to react. But because the activation energy has gone down, that means that more of these guys have enough energy to react. So these will buzz around and eventually hit each other and react. And so this could have taken the same amount of time because the temperature's the same, the pressure's the same, the concentration's the same. But in that same amount of time, we've produced one molecule here and we've produced two molecules here. So effectively, the rate of reaction has doubled. And a catalyst can increase the rate of reaction way over double. It depends on which reaction. The most efficient catalysts are the biological catalysts. Just do that in green. Biological catalysts, or biocatalyst, and they are known as enzymes. Enzymes. Our bodies contain loads of enzymes and they are responsible for speeding up the rate of many of our reactions. We would die if we didn't have these enzymes because our metabolic functions would occur too slowly. And so these enzymes allow us to keep our body temperature where it should be at 37 degrees Celsius. That's good for those enzymes. And it also means that the reactions can occur quickly. If we raised our body temperature to like 300 degrees, reactions would occur quickly, but we would obviously die at that temperature. So we can't increase our pressure too much because that will kill us as well. We can't increase our temperature too much because that will kill us. And so adding an enzyme allows our reactions to actually occur. Okay, so there are way more examples. We could go into various different reactions and how increasing pressure, concentration, temperature, adding a catalyst, increasing the surface area. We could go into how all of that affects different reactions, but it's going to take a long time. So I hope you have learned something from this. I hope it's cleared up why the certain different conditions are going to increase or decrease your rate of reaction. So please do send me an email or write a comment below if you have any questions, and I look forward to seeing you in the next video.